In this video, I'm going to talk about partition coefficient. Now, what is partition coefficient? Now, as an example, we will consider ammonia. Now, ammonia, it is soluble in water, that is in the aqueous medium, as well as it is soluble in any organic solvent. For example, we can consider benzene or trichloromethane. But you will also observe that this organic solvent and the water, they are immiscible with one another, that you can see that there is a separate layer. That means they don't mix in one another. And if you take some amount of ammonia in the aqueous medium, and this is the separating funnel, and if you add some amount of organic solvent into it and then mix the two thoroughly, then after some time what's going to happen, some of the ammonia from the aqueous layer would go into the organic layer, and after some time an equilibrium would be established, so that the concentration of ammonia in the aqueous layer as well as the concentration of ammonia in the organic solvent becomes constant. And then what we are going to do is that we are going to find out the ratio of the concentration of ammonia in the organic solvent to the concentration of ammonia in the aqueous layer. And this ratio is called as the partition coefficient of ammonia between these two solvents. Now, what I'm going to do is that I'm going to solve a question uh, which has been put up in the A-level chemistry paper. So you will understand that how does it work. See, the question says what is meant by the term partition coefficient, which I already explained. Now see, here it says that ammonia is soluble in both water and in organic solvents, and an aqueous solution of ammonia is shaken with the immiscible organic solvent trichloromethane. The mixture is left to reach equilibrium. Now samples are taken from each layer and titrated with dilute hydrochloric acid. Now you take 25 centimeter cube sample from the organic layer and titrate it with hydrochloric acid. Similarly, you take 10 centimeter cube of the sample from the aqueous layer and titrate it with hydrochloric acid, whose concentration is known, and its concentration is 0.100 mole per dm cube. And this is what I have now shown in the adjoining diagram, that see, this is what we have got. So we have taken 25 centimeter cube of the sample from this organic layer. Suppose we have taken it in a conical flask, added a suitable indicator, and then we have titrated it against hydrochloric acid. We have titrated it against hydrochloric acid. As you can see, we have taken it in the burette, and the concentration of hydrochloric acid is 0.100 mole per dm cube, and we require 13 centimeter cube of the hydrochloric acid for the complete titration of this sample. So with this data, we can work out the number of moles of the hydrochloric acid as well as the number of moles of ammonia. As you can see that they react in the ratio of 1:1. Now let us work out how many moles of hydrochloric acid were present. So you know this formula, that the number of moles of the hydrochloric acid can be calculated by using the C into V relationship. The concentration is 0.1 and the volume that we used is 13, and to convert it into dm cube we divided by 1000, and it gives me 1.30 into 10 raised to minus 3 moles. That is the number of moles of hydrochloric acid. Now the number of moles of ammonia must also be the same, because they react in the ratio of 1:1. But we need to know the concentration of ammonia, so we divide it by the volume. Now, how much volume we had taken? We had, if you remember, that we had taken a volume of 25 centimeter cube. So this is the volume 25 centimeter cube that we had taken. So the concentration is divided by the 25, and we further divided it by 10 raised to 3 to convert the centimeter cube to dm cube, and we got this value 1.30 divided by 25. So this is the concentration of ammonia in the organic layer. In the same way, we can work out the concentration of ammonia in the aqueous layer, and using the same relationship, we find out the number of moles of HCl, C into V, and we had used 12.5 centimeter cube of the HCl for the second titration, and we got the number of moles of HCl. The number of moles of ammonia is the same because 1:1 ratio, but we need to know the concentration of ammonia, and we had taken 10 centimeter cube of the ammonia for this particular titration. So to know the concentration, we divided by 10, converted into the dm cube, and we get 1.25 divided by 10. That is the concentration of ammonia in the aqueous layer. Now we have got both the concentrations. We got the concentration of ammonia in the organic layer, 1.3 divided by 25. We got the concentration of ammonia in the aqueous layer, 1.25 divided by 10. The ratio turns out to be 0.416, which is the partition coefficient of ammonia between the organic and the aqueous layer. So which clearly indicates that ammonia is actually more soluble. See, it's more soluble in the aqueous layer than in the organic layer. So this actually tells us how ammonia gets distributed between the two layers. That is how we have to work out the concentrations. Now the second part of the question is that what would happen to the value of K partition if instead of ammonia we use butylamine, right? So just think about it, what's going to happen, right? What's going to happen if we use butylamine? Now butylamine has a non-polar group. Butylamine is C4H9NH2, and this the C4H9 is the hydrocarbon radical, which is non-polar, right? And water is a polar solvent, so the solubility of butylamine and water would be less, so the concentration of ammonia in the aqueous layer would be less. So in our calculation, the denominator that we had got 0.125, that would also become less, so that the partition coefficient would increase. So this is one method for the working of the partition coefficient, and hope that you understood. In my other videos we will discuss more about the partition coefficients. Thank you very much.